Free space optical communication is an optical communication technology that uses light propagating in free space to wirelessly transmit data for telecommunications or computer networking. Free space means air, outer space, vacuum, or something similar. This contrasts with using solids such as optical fiber cable or an optical transmission line. The technology is useful where the physical connections are impractical due to high costs or other considerations. History. Optical communications, in various forms, have been used for thousands of years. The ancient Greeks used a coded alphabetic system of signaling with torches developed by Cleoxenus, Democritus and Polybius. In the modern era, semaphores and wireless solar telegraphs called heliographs were developed, using coded signals to communicate with their recipients. In 1880, Alexander Graham Bell and his assistant Charles Sumner Tainter created the photophone at Bell's newly established Volta Laboratory in Washington, D.C. Bell considered it his most important invention. The device allowed for the transmission of sound on a beam of light. On June 3, 1880, Bell conducted the world's first wireless telephone transmission between two buildings, some 213 meters apart. Its first practical use came in military communication systems many decades later, first for optical telegraphy. German colonial troops used heliograph telegraphy transmitters during the 1945 Hero genocide in German Southwest Africa, as did British, French, US or Ottoman signals. During the trench warfare of World War I, when wire communications were often cut, German signals used three types of optical Morse transmitters called Blink-Gerät. The intermediate type for distances of up to 4 km at daylight and of up to 8 km at night, using red filters for undetected communications. Optical telephone communications were tested at the end of the war, but not introduced at troop level. In addition, special Blink-Geräts were used for communication with airplanes, balloons, and tanks, with varying success. A major technological step was to replace the Morse code by modulating optical waves in speech transmission. Carl Zeiss Jena developed the Lichtsprechgerät 8080ths that the German army used in their World War II anti-aircraft defense units, or in bunkers at the Atlantic Wall. The invention of lasers in the 1960s revolutionized free space optics. Military organizations were particularly interested and boosted their development. However, the technology lost market momentum when the installation of optical fiber networks for civilian uses was at its peak. Many simple and inexpensive consumer remote controls use low-speed communication using infrared light. This is known as consumer IR technologies. A recently declassified 1987 Pentagon report reveals free space lasers have been mounted on Israeli F-15 fighter jets for the purposes of surveillance, missile tracking, and targeted weaponry. Usage and technologies. Free space point-to-point optical links can be implemented using infrared laser light. Although low data rate communication over short distances is possible using LEDs, infrared data association technology is a very simple form of free space optical communications. On the communications side, the FSO technology is considered as a part of the optical wireless communications applications. Free space optics can be used for communications between spacecraft, but this has not been put into practice. Current market demands. The demand for a high-speed and long-range FSO system is apparent in the marketplace. In 2008, MRV Communications introduced a free space optics-based system with a data rate of 10 GB per second, initially claiming a distance of 2 km at high availability. This equipment is no longer available. Before end of life, the product's useful distance was changed down to 350 meters. In 2013, the company MOSTCOM started to serially produce a new wireless communication system that also had a data rate of 10 GB per second as well as an improved range of up to 2.5 kilometers. but to get to 99.99% uptime, the designers used an RF hybrid solution, meaning the data rate drops to extremely low levels during atmospheric disturbances. LightPoint offers many similar hybrid solutions to MOST-COM's offering. Useful distances. The reliability of FSO units has always been a problem for commercial telecommunications. Consistently, studies find too many dropped packets and signal errors over small ranges. This is from both independent studies, such as in the Czech Republic, as well as formal internal nationwide studies, such as one conducted by MRV-FSO staff. Military-based studies consistently produce longer estimates for reliability. Projecting the maximum range for terrestrial links is of the order of 2 to 3 kilometers. All studies agree the stability and quality of the link is highly dependent on atmospheric factors such as rain, fog, dust and heat. Extending the useful distance. The main reason terrestrial communications have been limited to non-commercial telecommunications functions is fog. Fog consistently keeps FSO laser links over 500 meters from achieving a year-round bit error rate of 99.999%. Several entities are continually attempting to overcome these key disadvantages to FSO communications and field a system with a better quality of service. DARPA has sponsored over $130 million USD in research towards this effort, with the ORCA and ORCLE programs. Other non-government groups are fielding tests to evaluate different technologies that some claim have the ability to address key FSO adoption challenges. As of October 2014, none have fielded a working system that addresses the most common atmospheric events. FSO research from 1998 to 2006 in the private sector totaled $407.1 million, divided primarily among 4 startup companies. All 4 failed to deliver products that would meet telecommunications quality and distance standards. Terrabeam received approximately $226 million in funding. AT&T and Lucent backed this attempt. The work ultimately failed, and the company reorganized in 2004. AirFiber received $96.1 million in funding, and never solved the weather issue. They sold out to MRV Communications in 2003, and MRV sold their FSO units until 2012 when the end of life was abruptly announced for the Terrascope series. LightPoint Communications received $76 million in startup funds, and eventually reorganized to sell hybrid FSO RF units to overcome the weather-based challenges. The Maxima Corporation published its operating theory in Science, and received $9 million in funding before permanently shutting down. No known spin-off or purchase followed this effort. One private company published a paper on November 20, 2014, claiming they had achieved commercial reliability in extreme fog. There is no indication this product is currently commercially available. Extraterrestrial. The massive advantages of laser communication in space have multiple space agencies racing to develop a stable space communication platform, with many significant demonstrations and achievements. To date, no laser communication system is in use in space. See laser communication in space. Demonstrations in space. The first gigabit laser-based communication was achieved by the European Space Agency and called the European Data Relay System on November 28, 2014. 4. The initial images have just been demonstrated, and a working system is expected to be in place in the 2015-2016 timeframe. NASA's Opals announced a breakthrough in space-to-ground communication December 9, 2014, uploading 175 megabytes in 3.5 seconds. Their system is also able to reacquire tracking after the signal was lost due to cloud cover. 5. In January 2013, NASA used lasers to beam an image of the Mona Lisa to the Lunar Reconnaissance Orbiter roughly 390,000 kilometers away, to compensate for atmospheric interference. An error correction code algorithm similar to that used in CDs was implemented. 6. The distance records for optical communications involved detection and emission of laser light by space probes. A two-way distance record for communication was set by the Mercury laser altimeter instrument aboard the Messenger spacecraft. This diode pumped infrared neodymium laser, designed as a laser altimeter for a Mercury orbit mission, was able to communicate across a distance of 24 million km, as the craft neared Earth on a flyby in May 2005. The previous record had been set with a one-way detection of laser light from Earth by the Galileo probe, as two ground-based lasers were seen from 6 million km by the outbound probe. In 1992, 7. Quote from Laser Communication in Space Demonstrations LEDs. In 2004, a visible light communication consortium was formed in Japan. This was based on work from researchers that used a white LED-based space lighting system for indoor local area network communications. These systems present advantages over traditional UHF-RF-based systems from improved isolation between systems, the size and cost of receivers, transmitters, RF licensing laws, and by combining space lighting and communication into the same system. In January 2009, a task force for visible light communication was formed by the Institute of Electrical and Electronics Engineers Working Group for Wireless Personal Area Network Standards known as IEEE 802.15.7. A trial was announced in 2010 in St. Cloud, Minnesota. Amateur radio operators have achieved significantly farther distances using incoherent sources of light from high-intensity LEDs. One reported 173 miles in 2007. However, physical limitations of the equipment used limited bandwidths to about 4 kHz. The high sensitivities required of the detector to cover such distances made the internal capacitance of the photodiode used a dominant factor in the high-impedance amplifier which followed it, thus naturally forming a low-pass filter with a cutoff frequency in the 4 kHz range. From the other side, use of lasers radiation source allows to reach very high data rates which are comparable to fiber communications. Projected data rates and future data rate claims vary. A low-cost white LED which could be used for space lighting can typically be modulated up to 20 MHz. Research published in 2009 used a similar system for traffic control of automated vehicles with LED traffic lights. In September 2013, Pure Li-Fi, the Edinburgh startup working on Li-Fi, also demonstrated high-speed point-to-point connectivity using any off-the-shelf LED light bulb. In previous work, high-bandwidth specialist LEDs have been used to achieve the high data rates. The new system, the Li-First, maximizes the available optical bandwidth for any LED device, thereby reducing the cost and improving the performance of deploying indoor FSO systems. Engineering details. Typically, best use scenarios for this technology are LAN-to-LAN connections on campuses at fast Ethernet or gigabit Ethernet speeds, LAN-to-LAN connections in a city, a metropolitan area network, to cross a public road or other barriers which the sender and receiver do not own, speedy service delivery of high-bandwidth access to optical fiber networks, converged voice data connection, temporary network installation, re-establish high-speed connection quickly, as an alternative or upgrade add-on to existing wireless technologies, especially powerful in combination with auto-aiming systems. This way you could power moving cars, or you can power your laptop while you move, or use auto-aiming nodes to create a network with other nodes, as a safety add-on for important fiber connections. For communications between spacecraft, including elements of a satellite constellation, for inter- and intra-chip communication, The light beam can be very narrow, which makes FSO hard to intercept, improving security. In any case, it is comparatively easy to encrypt any data traveling across the FSO connection for additional security. FSO provides vastly improved electromagnetic interference behavior compared to using microwaves. Technical advantages: ease of deployment. Can be used to power devices. License-free long-range operation. High bit rates. Low bit error rates. Immunity to electromagnetic interference. Full duplex operation. Protocol transparency. Increased security when working with narrow beam. No Fresnel zone necessary. Range limiting factors for terrestrial applications. The principal limiting factors are fog, beam dispersion, atmospheric absorption, rain, snow, terrestrial scintillation, interference from background light sources, shadowing, pointing stability and wind, pollution, smog. These factors cause an attenuated receiver signal and lead to higher bit error ratio. To overcome these issues, vendors found some solutions, like multi-beam or multi-path architectures, which use more than one sender and more than one receiver. Some state-of-the-art devices also have larger fade margin. To keep an eye-safe environment, good FSO systems have a limited laser power density and support laser classes 1 or 1M. Atmospheric and fog attenuation, which are exponential in nature, limit practical range of FSO devices to several kilometers.